Gaël Delbary with Lustre on cloud drives.
Gaël worked at CF from 15 years in HPC division. During the first 7 years, he was a system administrator in Linux Windows environment. In 2015, he joined the HPC storage team as a storage administrator, and from 5 years, he's in charge of the next storage architecture for supercomputer R&D on HPC storage platform and L3 support on storage cluster. From 1 year, he is HPC storage leader.
Thank you. So I am sorry, it's the latest talk of the lad. My mission is to keep an eye with me up to the end. So that's the strange talk about clone drives. We are going to figure out which are clone drives in Lustre environments. So to figure out this, I'm going to start to give you some numbers of an old file system we have, and then we switch to ask, can we save this file system or not? And if yes, is it still a good position or not? Live or and let die? We will see. My file system, I am the file system, so my users love me. Why they love me? Because I am not purged. That's pretty cool for the users, but quota are enforced, of course. The big feature I have is that this file system is mounted on all compute nodes. To be honest with you, in this slide you have to remember 3 numbers. The first one is the number of drives we have, 1,300 HDD drives. It's Seagate drives, why not? We have 300 millions of inodes and a capacity about around 6 petabytes. That's the number you have to remember. Okay, but a file system is making to live. Okay. So what can we do to be better? We can rely on DD-Rescue. DD-Rescue is a crazy tool like Lustre. If you want to know a bit deeper, you can do many things. So what we did is that we can run some smart paths. And after 3 weeks, we were able to recover 98% of the disk, which is pretty interesting. Unfortunately, 3 days later, MD Alien kills the drive because the drive was not enough to read anymore. I have revived the drive, but I am unable to get more than 30%. So the drive was pretty bad. It's not finished. Okay, cool. We have Red Pool fully diluted, 38 drives. Of course, when a read occurred on a red group where there is only 7 red chunk, LSKFS panic. But the cool thing is that we had a backup up to 98.2% of last failed drive. So we have a good picture of this drive. What we can say is that, okay, we can insert this drive on the red pool. That was what I did, that was mine. So I did it, and I fully corrupted LDiskFS device. So it was not pretty cool because we were unable to mount the LDiskFS volume. We have many block descriptors corrupted. With the binary analysis, so a great tool on this is that the dump2fs tools, which give you some hints of what is going on. And after that, we go deeper and deeper, and we did the binary analysis of what is going on. And we have seen that we have a bitmap block in group descriptors. So and vice versa. So in fact, in ext4 or LDiskFS anyway layout, you have some block descriptors, and you have also bitmap to tell you, for example, the block is used or not used anyway. So in binary, it's pretty easy to see this. And that was a nonsense. That was unbelievable to understand the fact. So we can rely on Auto-FSK, which is pretty strong to do this. But we fall on two specific modes. Is that when we use LDiskFS, we use, of course, some ext4 feature like MetaBG. And when you have MetaBG, in fact, Auto-FSK is working differently when you want to read the first backup of group descriptors, the second, etc. We can talk a bit more in deep, but the time is going on. So we have found the root cause. The root cause is that when I did this, I have missed to check the kernel version we are running, which is a pretty old one, 7.6. And unfortunately, the sector size was 512 bytes. That was not working pretty well with MDRED, where there is an incompatibility with this. And the fact that the corruption was pretty heavy is that the resync was started when the red pool was assembled. Great. But what can we do? We can trust Auto-FSK, but we can ask to Lustre, Lustre, can you save Lustre? So we are doing Lustre on Lustre through loop devices. So that's another idea, is that we need to do strong analysis, deep analysis of what is going on. We have many billion of files which are corrupted. So unfortunately, we need to have some time to work on this. So go to loop images. The main idea is that we have a noisy servers which normally rely on block device. Here, block device, which is a web device in this case, but we remove that and we insert many loop devices which are stored in a Lustre file system. So the CA Lustre file system. So we run 38 DD-RESQ parallel. 24 hours later, all DD-RESQ has finished with some issue and some, of course, sector was not readable, but anyway, you need the exercise to go back to files and to check if we have a corruption or not. But as you can think, there is, of course, a big performance earned on this. But it was sufficient for our users. We were close to 1 gigs. Well, it was enough. The optimal bandwidth is close to 4, so there is a major impact. But it gets time to analyze the file corruption. What we did, I'm speaking about corruption, but when you have corruption and silent corruption, how do you do that you have a corruption? Because it's silent. Thanks to Robinhood, we have a SHA-1 policy where we store in databases all the SHA of the files on the file system. It means that we have a good picture of what was the files before the incident. Remember also, all files are in a read-only mode, so there is no modification on the integrity. Great. The good news of this is that we have close to 10,000 of file corrupted. Great, but can we do better? Yesterday, you have understood that to make a good wine, we take a piece of Merlot, you take a piece of Cabernet Sauvignon, and so on. And finally, you have tasted a good wine. Okay, that's exactly the same idea. But it's not wine or grapes, but it's El Discafés images, okay? And to do this is not magic. You have to understand where is your corruption and which part of your red chunk pool is missing. When you have understood this, you can play a bit. And to do this, we have revival all the drives we have, included the two first, which was killed. Okay, there is some issue. It's not trivial because in MD, IDM, MD Red, you have some security. For example, you have some timestamp and so on, some events, which is some counters that increase and increase. But anyway, you can play with loop devices. For your information, when you do this, we use about 400 terabytes of data, 40 drive about 10, okay? And when we play, we go up to 2 petabytes when you take the best blend, if I can say, okay? But we achieve to find a perfect combination. And the perfect combination was, okay, we have had so many information on this case, and we know that when the stack process, the stack read is going on, it will recover the data correctly. But we have still a major corruption on bitmap, for example, and we can rely on a 2FECK. Okay, it's job. Okay, great. But it restores, and it restores many files in lost place form. You have to understand that in this crazy situation, you have many files in lost place form. It means that you have to move on the white place the file that was on a lost place phone. We need to do some modification of the files to tell to Lustre, to El Discafés, oh, it's a good object, look like, it's fine. Okay, so the result is we have only 6 files which was corrupted. Okay, 5 minutes. I'm going to take my best. But unfortunately, after having replaced 100 drives, we haven't received any drives. So file system is going to die. And what you have to think is that the time plays against the production. Because as you know, more you are waiting, more the probability is increasing. Okay, to have an unreadable sector. Go bye-bye. Okay, no drive, not able to save file system. Okay, that's the life, but it's pain, of course. But we can adopt a different strategy. Can we take a read useful strategy? I mean, read useful is that we are not ready to replace all block drives, but can we do let the red stack do its job? It means that just compute what we are doing when you read files. Okay, but it's both tricky when you are unable to read, of course. The third parameter is the number of the file system. The number of inodes. It's a big, huge. So to get many information, we use parallel LBHDU tools, which are scaling pretty well, like MariaDB and this. Okay, and we have also to limit the prediction impact. So we have a workflow to build. Anyway, no time to die. We have to rely on some tools. Ruby-Roon, of course, because as I haven't mentioned, we have 36 million of hard links. That's a pain when you want to migrate this. Anyway, we want to trust LBH, for example, for the hard link list. We have to rely on resync for sync hard links, and of course MPI fidelity to sync data. We have some issues. The first issue is that async doesn't scale in hard links mode. It's pretty slow. It's mono-thread, if I can say. The second behavior is that Ruby-Roon, there is a MySQL procedure in this, and the resolution is slow. Okay. Third one, MPI fidelity doesn't support hard link, and there is an issue when he copied Lustre XTTR, which is a bit a bad thing. Okay, what we did is that MPI fidelities, we did a patch to ignore hard links, and to build Red Hat 8, build on Red Hat 8, sorry. I am sorry, it's not yet upstream, but it's going on. About Lustre XTTR, it was, here was a patch, I have written the commit, but if you jump to the latest release, you have the patch. In Ruby-Roon, okay, you have a great MariaDB with the hard links. Great. What we are going to do is that we have a better solution in Lustre, which is the fit to pass, LFS fit to pass command, where the complexity is pretty small, because you have to pass a kind of pass, and it resolves all hard links in one command, and it scales pretty well. We achieved 36 million in 2 hours, so it was not good. It was in parallel, of course. And what we have seen is that rsync is pretty efficient when you give him one file. Okay, one feed file, one file. Sorry, there is a mistake. Is because on our configuration we add up to 20 maximum hard links per file, so which is pretty efficient. And of course, with that, when we have one file per feed that contains all hard links, we can run multiple rsync. Okay. On these cases, we add close to 2,000 rsync in parallel to synchronize the hard links. Okay, great. I have written is a macro step to do the operation on production. That's just for information, but what we need to note is the performance we achieve is about 100 millions inodes in 8 hours, which was good for our production. So to conclude this, we have successfully copied the file system. You have, I think, you know perhaps already, but the versatility of Lustre. We can do many things. There is also pretty strong parallel open source tools, and you have to monitor your IDD also. At CA, we have an AI model running on this clone drives. So why clone drives also, if you can have a kind of picture of this, is that, I don't know if you know the vegetable manioc, that's a bit of fat that go on the track, on the drives, and the track was not readable. Okay. Then we have some issues. I haven't any time to talk a bit more, but we fall into the pass 1D multi-claim block research in TFCK, where we are going to have 1 year to finish. In the beginning of this, we have figured out how to fix this quickly kill the sad files. Okay. We have also some NBLock issue when you are going to fill up pretty quickly drives, and then LTune disk, which is a killer when you have many UDEV rules which was triggered, it kills the file system because LTune disk is doing a debug phase. Catastrophic mode, and it reads 4K on all servers and all volume, which is pretty painful. We have also the read-only mode, MPF LUTs with Lustre X ATTR, and to finish, we fall into a slot memory corruption due to the usage of FE map. It's just for latest Lustre version, LTS version. Thanks.
So, yeah, okay.
First of all, I want to say such amazing things can be done on LDiskFS backend. I wonder whether such things can be done on other backends. So LDiskFS rocks. And there is a question. There was about MetaBG during FICK, so some issue you said. So MetaBG has its own format. There is a copy of block groups as the second and last group. And there is special functionality in dump E2FS that allows us to point to this group.
You can see like one file is outlinked.
I miss the second question. I'm starting with the first. Okay, with the first is the main issue with RBH v4 is that the way that the resolution of the path is doing. Okay, when you want to take a file which is at 5 days in a tree, you need to get information about all the level of your tree. Okay, so when you need some hard links, you need to get all hard links because it's one entry in RBH, but okay, it's one hard link, but it's one entry. It means that for each entry, you need to resolve the path because it is what you want. So there is a procedure in MariaDB, in MySQL, I have said, but we can't do better because that's the way that MariaDB is doing the resolution. Okay, what we did is this. I am sorry to tell you, but that's not a patch. That's another way to get a short answer of what we would like.
Okay, and the second question was about like your experience with hard links on, for example, these file systems.
Yeah.
What is the number of times the inode have been hard linked? The maximum or the average you are used to see? I'm just wondering, like on other file system, what are we used to see? Because on some file system I have, like we have like hundreds or thousands of hard link on the same inodes. So as you say, like it doesn't fit in the extended attribute, and then Robin is trying to resolve this 1,000 times. So you get it, it's stuck, and then Robinhood is not working for hours.
Yeah, it's
so what are you used to see on your file systems?
It's only 20, I have said. Okay. But I don't remember, Andreas, when you get. I don't remember the limit of the extended attribute. 60.
160 hard links with reverse.
Okay, so if you go up to this, you take another block to store this. How does it work?
So the reverse hard link information is stored in an extended attribute, and we put an arbitrary limit of 160 or something like that, reverse links onto each file, just to make it not consume too much space. You could actually store, probably 1,000 or something like that. It just gets more slow, and most people don't ever have that many links with one file.
Except on this system. Yeah, that's users. Just one thing to bring to you. I don't know if it can help. The issue was specific to a climatology workload. Okay, they use it to make up. Okay.
Okay, so the last questions before the wrap up.
Thank you. Very interesting talk. So, as I understand it, most of this talk relates to recovering from LDISC-FS. How much of this is relevant if you have like ZFS as your backend on a primary, or for example, if you have something like a total MDT failure?
I have no idea. We have. I am sorry. We have no ZFS also. Sorry.
Okay, thank you, Gaël.